In the previous video, we looked at homogeneous nucleation and heterogeneous nucleation. Now we're ready to move on to the growth part of solidification. We will start from the simpler case without considering heat transfer. There are two types of growth. One is called continuous growth, and the second is called lateral growth. Continuous growth is something more common. Let's draw the solid-liquid interface. On the left, it's all solid, and on the right, it's all liquid. During the growth process, it can be viewed as the atoms from the liquid phase, they hop from the liquid phase into the solid phase. To be more precise, you actually have atoms going from liquid to solid as well as from solid to liquid. However, during solidification, you have more atoms hopping from the liquid phase into the solid phase, which lead to the advance of the solid phase interface into the liquid phase. Next, let's look at the thermodynamics of continuous growth. Mathematically, it can be expressed by delta G equals to L over Tm times delta Ti. Delta G is the driving force for solidification. L is the latent heat of melting. If you recall from one of the previous videos, heat will be released when a material turns from liquid into solid. And this amount of heat is called the latent heat of melting. Tm is the melting point. Delta Ti is an important term. It is called the undercooling. You will see undercooling many times in the future videos. You may wonder what is undercooling. Undercooling is that we need to either globally or locally lower the system temperature to ensure the growth of the solid phase so that it can overcome the energy barrier we saw in the last video when discussing the homogeneous and heterogeneous nucleations. Assuming the melting point is 100 degrees, if your system is at 99.9 degrees, then 0.1 degree is the undercooling. After looking at the thermodynamics of continuous growth, we can look at the kinetics. Here we have nu equals to K1 delta Ti. Nu is the growth rate. K is a constant associated with the interface mobility. Delta Ti is the undercooling. As you can see, as you increase the undercooling, the growth rate increases. For the continuous growth to happen is pretty easy. You don't need a large undercooling. Usually a fraction of 1 degree is good enough. The second type of growth is called lateral growth. Lateral growth happens on very flat surfaces. In this example, we have the liquid phase on the top and the solid phase down the bottom. If we zoom into the interface area, we can draw the solid phase as arrays of atoms. And here is the solid-liquid interface. During the growth process, you have that one atom solidified on the surface. Because of the dangling bond, as well as to minimize the surface energy, the atoms will adhere on the new surface and grow laterally. And this advances the liquid-solid interface by one atomic layer. And this process is called lateral growth. If we look at the kinetics of lateral growth, nu, the growth rate, is proportional to e to the power minus k2 over delta Ti. And k2 is a constant associated with the boundary mobility for those lateral growth. Delta Ti is the undercooling. Again, as you can see, if we increase delta Ti, nu increases. Compared to continuous growth, the lateral growth requires a larger undercooling. This indicates that the lateral cooling is more difficult to activate and it requires a lower temperature, that is higher undercooling, to promote it. Here is a graph that plots the growth rate as a function of undercooling for both the continuous growth and lateral growth. Continuous growth is simply a straight line and it requires nearly no undercooling. And here is the curve for the lateral growth, and you can see that requires a larger undercooling. In both cases, larger the undercooling, higher the growth rate. In addition to lateral growth on superflat surface, it can also happen on screw dislocations as well as twin interfaces, which we'll not discuss in details in this video. Here is one example of lateral growth published by Maliaco and co-authors in ACS Nano. The example here is not solidification, but shows the same principle for lateral growth. You can see the growth of the nanowire is layer by layer, which can be explained by this lateral growth mechanism. In real world, we rarely see continuous growth and lateral growth in physical metallurgy. The predominant microstructure is the dendrite structure. On the left is an example of the copper tin dendrites. After solidification, you get those long dendrite structure. Not only they can grow in one direction, you have secondary and tertiary dendrites branching out. To simulate and to compute the dendrite formation, you can use phase field modeling as shown in the example on the right. The question we like to answer is why do we have dendrite formation during solidification? The key is the heat flow, which was ignored by the continuous growth and the lateral growth. Let's create a system. On the left, that's solid, and on the right, that's liquid. And the interface advances into the liquid phase. Let's also look at the temperature profile of the system. One very important thing is that temperature is not uniform in the system. The bulk solid phase and liquid phase are at a lower temperature compared to the region adjacent to the interface. This is because as the liquid phase turns into the solid phase, excess amount of heat will be released as the latent heat. This heats up the material locally, but will eventually conduct it away by the system. Before the heat can diffuse away, if at the liquid-solid interface we have a little bump forming, the bump ventures into a region that has a lower temperature compared to the rest of the interface. To the right, it's at even lower temperature, and this drives the little bump to grow into a dendrite. And this explains dendrite formation in solidification and why the dendrite microstructure is predominant in the cast metals. Dendrite structures are also commonly found in welds, especially in the fusion zone, as well as 3D printed metals. One thing I'd like to draw attention to is that in most of the cases, the dendrite growth has a preferred crystallographic orientation. In cubic metals, the growth direction is usually 001, as you can see in many superalloys. For HCP metals, the growth direction is usually 101/0. Before we finish today's video, we'll quickly discuss why dendrite formation can lead to hot cracking in metals. This is something I recently learned from Professor Wen Chen at UMass Amherst. He's an expert in 3D printing. Hot cracking are widely observed in welds as well as in 3D printed metals. In this example here, we have the primary dendrites forming. The secondary dendrites can also form. In the region highlighted in red here, it is still liquid, and it is confined by the neighboring dendrites. If we cool down the system further, the liquid phase will also turn into solid. During the phase transformation, there is a volumetric shrinkage because the solid phase has a higher density compared to the liquid phase. The combined effect of that is trying to shrink as well as is confined in volume leads to cracking, and this cracking is called hot cracking. Hot cracking is detrimental to the welds as well as 3D printed metals. In this video, we looked at growth, especially continuous growth, lateral growth, as well as dendrite formation and dendrite formation's impact on hot cracking. Everything is centered around pure metals. In the next video, we'll look at the growth mechanism of alloys.